In this lesson, we'll talk about the angles in different kinds of polygons. Hexagons, pentagons, octagons. What do they add up to? We'll talk about inscribed quadrilaterals, what it means to be inscribed, and what's special about quadrilaterals that are inscribed. And we will talk about what does it mean if we have fractions for our exponents, if we have x to the 1/3, or if we have, let's see, what do I want to do? 8 to the 2/3, or 7 to the 1/4. What does it mean when we have exponents as our fractions? So first, let's begin with some vocabulary that we will need. We've already talked about interior and exterior angles before, but we had a triangle, and we took one exterior angle, and its measure was the sum of the two remote interior angles. So you've seen this before. We've got the interior ones on the inside, exterior on the outside, if we extend one side of the polygon to get that exterior angle. If we want to talk about inscribed, that means we have a shape that is inside of a circle. So here's my circle, and then I put some kind of a shape inside of there. It could be a triangle, it could be a pentagon, it could be a square. We are especially going to talk today about ones that have 4 sides, but they don't have to be anything special about them. They don't have to be rectangles or squares or anything, just a quadrilateral. What it means to be inscribed is that the polygon's completely inside the circle, and every single vertex is on that circle. So if I do one that is something like that, that one is not inscribed because that lower left vertex misses the circle and is not actually on it. So this one would not work. So let's start talking about what's going on with these things. If you have a convex polygon, let's take one exterior angle at each vertex. Does not matter if we take a triangle, if we take a quadrilateral, if we take a decagon, if we take a dodecagon, if we take a polygon with 100 sides. If we take one exterior angle at each vertex and add them up, we will always get 360 degrees. So going back to this picture over here for a moment, if I were to take this exterior angle plus this exterior angle plus this one, all 4 of those green ones, add them up, I get 360. If I start doing more than one at a vertex, if I say, oh, well, at this vertex, I'm also going to extend this side, so I'm also going to use that exterior angle. Don't have the 4 I already drew. Those add up to 360. Throw in this extra one, and it's more than 360. So it's just one at each vertex that we're talking about. So thumbs up, are we good with that question? I'm going to. But does that make sense on the idea of that? One exterior angle at each vertex, add them up, and we will always get 360 degrees. So I could take some sort of a triangle, and I could take one exterior angle at each vertex, add those up, and I'd get 360 degrees. With interior angles, what do they add up to for a triangle? Come on, you guys know this, everybody. They add up to 180. What if I take, I'm going to pick a special quadrilateral because I know you know how big its angles are. What if you add up the angles of a rectangle? Do you still get 180? What do you get? 360, because you know they're all 4 of them are 90. So if it's interior angles, it's going to depend on how many sides it has. If it's a triangle, it's going to add up to 180. If it's 4 sides, we're going to see. You know, if it's a rectangle, it's got to add up to 360, but we'll see about the other quadrilaterals. And pentagons, and 12-sided figures, and so on and so on. So to do that, we'll start with the one that we know. We know that a triangle, the angles add up to 180. So then for the other figures, so let's start with 4. We know if these were right angles, they'd all add up to 360. Let's see what happens with this one. We're going to pick one vertex and draw as many diagonals as we can that start at that vertex. Doesn't matter which vertex I pick, but I'm only going to draw the diagonals from one vertex until I've drawn all the possible diagonals that I can. So, looking at this quadrilateral, where we had 4 sides, when I did that, how many triangles did I draw? Everybody? 2 triangles. So let me color those in. And this triangle, I know that these 3 that I've just shaded in red have to add up to how much? 180. Okay, let me color in the angles in the other triangle. What do these blue angles have to add up to? Now, if I put all the reds and blues together, have I completely colored all 4 vertices of the original quadrilateral? Have I colored anything extra? Anything weird in the middle or something? So all I have to do is put the 180 and the 180 together, and for the rectangle that you knew, and for any other quadrilateral, these have to add up to 360, because I got 2 triangles, so I had to do 2 times 180. Okay, moving on to my next picture, I took a vertex, drew as many diagonals as possible. I started off with 5 sides. How many triangles did I get, everybody?
3.
So I had 3 triangles. If I do the same thing, if I shade in all of the angles of one, that's 180 degrees. If I shade in all of the angles of another one, that's 180 degrees. If I shade in all of the angles of the third one, that's another 180 degrees. Have I shaded all 5 angles of the original pentagon? Anything shaded too much? Any extra? So it's exactly 3 times the 180. Sorry. Or 540 degrees. Okay, if I had 6 sides over here, how many triangles did I get? So how many 180s am I going to have? So for 6 sides, I'm going to need 4 times 180, or 720 degrees. Let's see if we can make a prediction now. What if I had 98 sides? I wonder what they're going to add up to. Can you look at this and come up with any prediction that will become our formula? If you know how many sides you have, can you figure out how many triangles you have, so that you can figure out how many 180s you need? Does anybody see a pattern of how that works? If you take the number of sides, how do you get the number of triangles? What do you think? So for every side, what? Okay, so I could say, oh, well, I have 4 times 180, then I'll have 5 times 180, 6 times 180, 7 times 180. That will work if I'm not talking very many sides. But I really don't want to do it that way to get up to, well, how many triangles would I have if I had 98 sides? That's a long list to go through. So let's see if we can think of another way that also works for looking at the pattern. Is there a relationship between how many sides and how many triangles? Sir? What do you guys think? If you have 5 sides, 3 triangles, 6 sides, 6 minus 2, you have 4 triangles. So if I have 98 sides, how many triangles? So that would have to be whatever 96 times 180 would be. But we're really most interested in getting this down as a formula. So if we have n, and remember that top row is sides, we have n minus 2 triangles. So n minus 2 times 180 degrees. And that becomes our second formula for the day. The first one being exteriors add up to 360. So this means an n-gon means we have n sides. So n minus 2 triangles. So n minus 2 times 180 degrees. The first formula was if we take one exterior angle at each vertex and add all of those up, we get 360 degrees. Let's try this out with an example. If I have a 14-gon, so I have 14 sides, Elias, what will I need to do to get the sum of the inside or interior angles? So I need to take 14 minus 2 for the number of triangles, and then 180, so I'd be looking at 12 times 180, and I don't know about you, I'd punch that in on my calculator probably, and get 2,160 degrees for the sum of those interior angles. Now, let me point out a special case that you'll have a few problems along the way that ask you about. If they say it is a regular 14-gon, that means all the sides are congruent and all 14 of those angles are congruent. So I have 14 that are all the same. And they all add up to 2,160 in this case. So x plus x plus x plus x, they're all the same. 14 x's equals 2,160. How do I get just one of those x's? What am I going to need to do? And it only works if it's regular. I have to know they're all the same. And that's not going to be a real nice number. In this case, it would be 154 and 2/7 degrees for each angle. But that only works if it's regular, if you know that they're all the same. Otherwise, they could all be different, so there's no way of doing that. To finish this example, and you're going to have half a second to get ready to give me your answer. We've still got the 14-gon. What is the sum of the exterior angles? Everybody shout. 360. That didn't really sound like everybody, but questions for that? Okay, then we're going to move on to our inscribed quadrilaterals. So remember our definition, we have to have a circle. The polygon's completely inside of that circle, and all of these vertices are points on the circle. There's going to be something very special about this quadrilateral. It's not going to be true of just any old quadrilateral. But if it's inscribed in a circle like this, there's going to be something special about the opposite angles, like A and D, or like B and D, they're across from each other. Or A and C, we're going to talk about B and D. So, if I looked just at angle D up there at the top, what kind of angle is that? What? It's an inscribed angle. And don't we know something about an inscribed angle and the arc that it catches? Don't we know that the inscribed angle, so D, is 1/2 of that arc that it catches? And I'm going to write that arc's name as ABC to say go the long way around, start at A, go through B, and end up at C. If I just wrote AC, it would mean the shortest way possible. And that is true because that is an inscribed angle. Now I'm going to do the same thing with the opposite angle at B. Got another inscribed angle, right? So should be true that angle B is half of the arc that it catches. So that's what I'm going to write down now. That the measure of angle B is 1/2 of the arc ADC. I didn't really need the 3 letters in there, but just to emphasize what's going on with that. And that is because that is also an inscribed angle. Now to get to something special about those opposite angles, I'm going to add them together. I'm going to take the measure of angle D plus the measure of angle B. Well, I know D is 1/2 of ABC, plus I know B is 1/2 of ADC. Oh, looks like I got a GCF of 1/2, so I'm going to bring that out in front. And then I've got arc ABC plus arc ADC. And let's look at our picture and see what we've got there. So ABC is that up, right? And then to that, I am going to add ADC. So start at A, go through D, and end up at C. So when I put those two together, what do I have? I have the whole circle, so 360 degrees, right? So that means when I took those opposite angles, I got the 1/2 times the whole circle. So 1/2 times 360. Or 180 degrees. We took opposite angles of an inscribed quadrilateral, added them together, and we had to get 180 degrees. So that is your next formula to write down. It does not work to say A and C are equal to each other. Look at B and D. They don't look anywhere close to equal to each other. This does not say opposite angles are congruent. This does not work in just any old quadrilateral. It's got to be inscribed in order for this to work. So what this one said was take any opposite angles, add them together, and we have to get 180 degrees. So let's do this problem that uses this new information and reviews some stuff from before. Let's start with the new information. So we have a circle. We have an inscribed quadrilateral. Can we take opposite angles and help us get any of those letters that we are looking for in this one? So Brea, what do you think? Can we take any of the opposite letters and use that to help us? So tell me what and what. Slow down, just one at a time. 55 and X, and what do I do with the 55 and the X? So isn't that what our formula just said? Take two opposite ones, the 55 and the X, add them and we get 180. And our reason is because we have an inscribed quadrilateral, not an inscribed angle. So subtract 55 from both sides. And what do we have for X? Riley? 125. I think that's supposed to be a degree sign after the X there, so I'll just say X is 125. Do I have another set of opposite angles, Gabe? Besides the X and the 55, do I have another set of opposite angles in this inscribed quadrilateral? Well, look at it. We just did the X and the 55. So the 70 and the A, so what does that mean I can do with them? Add them, and what did our formula say we have to get? We had to get 180, so everybody, what is A? 110. Okay, then review. Now we have to get Z. Oh, it's this arc up here. But I don't have an inscribed angle that just gets Z, do I? So I look at other arcs that I've got. I've also got a 30. Can I put Z together with something and get an arc that's taught by an inscribed angle? Yep. So Z plus 30 has to be twice that inscribed angle, or the 55 is half of that arc. So if this is 110, everybody, what does Z have to equal? Questions from anyone on that? So moving on then to the last topic for today, if we're talking about fractional exponents. If we have x to a fraction or h to a fraction, the fraction of the exponent, the top part means the power, and the bottom part means the root. So if we start off with something like x cubed, that we already know what that means, that that's going to be x times x times x. If we think of that as 3 over 1, that means just take the single itself and cube it, we still have the x cubed. If we have a 1 in the numerator, 1 over 2 means the second root, so that means the square root. X to the 1/3 means the cubed root. X to the 1/4 means the fourth root. X to the 1/10 means the 10th root. If we have both of them, if we don't have a 1 either place, if we have something like x to the 2/3, that means we need to square it and we need to have the cubed root, and we can do that in either order. We can either take the cubed root first and then square it, that's usually easier, or we can square it first and then take the cubed root, and we get the very same thing. So numerator is power, denominator is root when we're talking about fractional exponents. So let's run through a few. The faster you guys help me go through these, the faster we'll get done with our notes. So a lot of this works just the same as with any old exponents. First off on this one, my exponent goes with whatever was typed right before the exponent. So the 27 gets this exponent. The negative sign out in front does not. So it still equals negative something. Negative exponents work just the same as they always have. So 27 to a negative means move the 27 from the numerator to the denominator and make the power positive. So I've got to put a 1 in as that placeholder. Now, what did I say to the 1/3 means? Leah, what did I say an exponent of 1/3 means? X to the 1/2 is going to be square root, so what's x to the 1/3 going to be? So we need the cubed root. Can you tell me the cubed root of 27? We'll put this together, -1 over the cubed root of 27. So what do I have, everybody? So the cubed root of 27 is 3. So this one becomes -1/3. They kind of do it a step at a time. The things you already know about exponents are still true. Next one, a little bit easier so I don't have the minus out in front. Once again, I have a negative exponent. So that means the 64 moves from the numerator to the denominator, and the exponent changes from negative to positive, and put a 1 in the numerator. Ada, what is 64 to the 1/2 going to be?
8.
Because that means the square root of 64 So we have 1 over 8 in that case. Okay, next one, let's have something that's not a 1 in there. Let's deal with a numerator and a denominator. So 64 to the 2/3. So the 2's the power, the 3's the root. Wonder which one's easier to do mental math. I want you to grab the calculators. Without the calculator, would you rather take 64 times 64, or would you rather try to figure out the cubed root of 64? How many would rather do 64 times 64? How many would rather mental math try to figure out cubed root of 64? When they ask you to do these without a calculator, they're going to come out nicely. So let's do it that way. Let's do the cubed root first, and then we'll square that answer. If we're doing it without a calculator, it's probably going to be 2, 3, 4, 5, 6, something we can do mentally. 2 cubed is how much? 2 times 2 times 2 equals? 8. What about 3 times 3 times 3? What does that equal? So cubed root of 64 isn't 2 or 3. Anybody come up with what times itself is 64? Ready? So 4 times 4 is 16. Times another 4. 16 times 4 is 64. So this cubed root is 4. And then we need to square it. So we end up with 16. And last one. So I've got a negative in there again. Negative exponents still mean go between numerator and denominator. So that means put the 125 in the denominator with a positive exponent. So 1 over 125 to the 2/3. Does that mean I take the square root and cube it, or the cube root and square it? What am I having to do in this case? Kara, can you help me? So I've got to do the cube root and square it. And would we rather do 125 times 125 mental math? Figure out cube root of 125. So let me write down what we're trying to do here. We're trying to take the cube root of 125 and then square that. Can anybody tell me the cube root of 125? Or everybody tell me? So that means we have 1 over 5 that we still need to square. So 1 over 25. Questions for today? So since we didn't do an example of this kind of problem, let's talk through number 18 together. So you see this figure. Do I have a circle? So is this that inscribed stuff that we were talking about? Nope. So look at where you have x's and y's in this figure. What kinds of angles have x's in them? Who can tell me what kinds of angles you see for the x's? Allie? They look like acute if it was drawn to scale, and probably they are, but not necessarily. Do we know something else about the kind of angles that we have there? Emily? They're exteriors. And what do we know about exterior angles now? Hayden? They're going to add up to 360. So what we want to do to solve this one is to start writing down our exterior angles. I don't care which one you start with. I'm going to start with the x, and then add another one. And then I need the 100 and the 45. And then I need the 57 and the 31. That hasn't gotten all of them yet. I still need the 90. And they all add up to 360. Then you've got a whole bunch of numbers here that you're going to combine, subtract from both sides, and you'll end up with 2x equals something. So then you can get x, right? Agreed? You guys can get x from here. Question? That would just be exterior angle sum. Find the reason on that. Then once you have x right here, will that let you somehow get y? Grayson, how are you going to get y now? What property are you going to use? A little louder. So whatever this number is for x, plus the y plus 40 is going to give you 180, and that will let you finish solving that one.